Hello everyone, welcome to this video evaluating the general formula for a K-form. Now in this video we will look at how to evaluate the formula for a general K-form in an n-dimensional space. This situation can occur when a K-dimensional surface is embedded in a higher dimensional manifold and we wish to integrate the K-form over this surface. Alright, now this has been the subject of some previous videos, but now I'm just going to focus on what form these K-forms can take. What's the general formula, how to use the general formula, and just some points about it. All right, so let's make a start. All right, better hide that. So the formula here, omega is this. We have sum sigma. N is equal to or greater than 1 up to K. So the K value is equal to or less than N. We have the function in front here. Okay, the coefficient function here. Then we have the wedge products of the individual differentials up to k of them. So this describes a general K-form in n-dimensional space where k is equal to or less than n. K is equal to or less than n. This K-form is a weighted sum of wedge products of k differentials dxi, k of them, where the weights qi1, i2, ik of the coordinates x1 to xn are smooth functions that depend on the coordinates x1 to xn. So dx1, dx2, up to wedge dxk, the wedge product of k differentials of the coordinate functions. This summation runs over all k tuples, i1, i2 to ik, with n equal to or greater than 1, so k is equal to or less than n. Maximum value k can have is, of course, n. So below, over the next couple of slides, we're going to have some concrete examples of specific cases of n and k. All right, so you can think of n as the n-dimensional space, and then the K-form is of equal to or less dimension. So you might be talking about a K-form that you're integrating over some k-dimensional submanifold within an n-dimensional manifold. And last couple of videos, we've done a bit of that. All right, next one. All right, so let's have a look at example n equals 3. We're in three-dimensional manifold, or three-dimensional Euclidean R3 if you want, or just 3 dimensions in general. We're going to look at the case k equals 1, so we're going to have a 1 form in 3 dimensions. 1 form on a 3-dimensional manifold. Right? Omega could be equal to k1 of the coordinate functions x1 to x3 dx1 plus q2 dx2 plus q3 dx3. This represents a standard differential 1 form in 3 dimensions. So for example, omega could be x1 dx1 plus e to the x2 dx2 plus sine of x3 dx3. Let's have a look at the case of a 2 form, k equals 2. Omega could take this form here. Okay, dx1 wedge dx2 times these coefficients here, plus dx1 wedge dx3 times these coefficients here, plus dx2 wedge dx3 times these coefficients here, where the coefficient function is a function of the coordinates in the space. So in this case, we're in n equals 3, 3 dimensions. So q could be made up of anything from x or x1, x2, x3 to some or all of the coordinates. It doesn't have to be all of the coordinates. We'll see that a little bit later as we go along. So for example, we can have omega of a 2 form, x1 times x2 dx1 wedge dx2 plus x3 times x3 dx1 wedge dx3 plus e to the x2 plus x3, the exponential of x2 plus x3, second and third coordinates summed together, the exponential of that, times dx2 wedge dx3. All right, let's look at case k equals 3, a 3 form. That's the highest form in this space because the space is n equals 3, n 3-dimensional space, and k is equal to 3, so you have the volume form. In this case, there's only one term because there's only one way to choose 3 indices from 1, 2, 3, where I1, I2, I3 lies between 1 and 3. So omega is q of 1, 2, 3 of x1, x2, x3, dx1 wedge dx2 wedge dx3. Okay, this is the 3 volume. Okay, and then these coefficients could be a function of any or all of these coordinates. So for example, omega could be x1 times x2 times x3, dx1 wedge dx2 wedge dx3. It could also be omega is just x1 times that wedge product, or x2 times x3 times that wedge product. Okay. Now let's look at example n equals 3 again. Case of a K4. Actually this should be n equals 4. I seem to have made a mistake there. N equals 4 because it goes up to 4 dimensions. So case, another typo. Case k equals 2, a 2 form. So omega could be q12 dx1 wedge dx2, q13 dx1 wedge dx3, plus other combinations, plus q34 dx3 wedge dx4. Let's have a look at an example. So for example, omega could be sine of x1 times dx1 wedge dx2 plus 5x3 times e to the x2 times the wedge product of dx2 wedge dx4. Remember, it's a 2 form. And so we can have combination 1, 2, 1, 4, 3, 4, 2, 4, 1, 3, all the rest of it. Okay, but instead we've got this version here. So there are numerous examples we can have, but I'm not going to fit them all in here. Not even begin to fit them. Case k equals 3, a 3 form. Okay, so omega could be q1, 2, 3, that plus q1, 2, 4, because remember in 4 dimensions of this, plus blah, 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 this. So for example, we could have omega as x1, x2, dx1, wedge dx2, wedge dx3, plus cos of x4, dx1, wedge dx3, wedge dx4, and of course, other combinations as well. Let's have a look at for n equals 4. Still in n equals 4 again. Case k equals 3, a 3 form on R4. So we're going to look at a 3 form on R4. So k equals 3 and n equals 4. All right, so omega could be q1, 2, 3, dx1, wedge dx2, wedge dx3, plus q1, 2, 4, all of that, plus blah, 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 others. All right. So for example, we could use omega as x1 times x4, dx1 wedge dx2 wedge dx3 minus cos of the third coordinate x3 times dx1 wedge dx2 wedge dx4 plus e to the x second coordinate x2 times the wedge dx2 wedge dx3 wedge dx4. All right, let's have a look at the role now of these coefficient functions. So the role of the coefficient. So the coefficient qi1, i2, iq of the coordinates function of the coordinates x1 to xn encodes the magnitude, which will affect when we integrate the size of their answer, the magnitude of our answer, and the functional dependence. I'll get to that shortly, of the K form, providing additional context for integration or computation. So these coefficients can be functions of the coordinates, but they could be functions of things like if we're dealing with fluid dynamics, it might be density. Now, density in turn would be a function of the spatial coordinates. All right, so there's other factors at work. It could be a function of time. It depends on what coordinates you're using. Okay, so magnitude, well, the degree or size of your answer in the end when you're integrating one of these forms over some space, over some manifold, and then the functional depends. It depends on what coordinates are involved. So get to that a little bit more. So this coefficient can in principle depend on all the coordinates of the manifold, regardless of which dxi appear in the wedge product. We've seen that. So for instance, up here we had the third coordinate for the coefficient here, but the third coordinate didn't appear in the wedge product. All right, and this is because the coefficient isn't part of the volume element itself. It modifies it by scaling or altering its contribution based on position. That's what the magnitude is, but also the functional dependence. So the independence between the wedge product and the coefficient is a feature of differential forms. So when you're integrating this object here, these coefficients will affect the magnitude of the final result. They're going to depend on the coordinates, some or all of the coordinates, or other components which may in turn be made up of the coordinates. So if you're talking about a flow of fluid over a surface or something like that, you're going to have things like the density, and the density in turn will be a function of some or all of the spatial coordinates and so on. All right, so the wedge product handles orientation and anti-symmetry, this bit here, the orientation and the anti-symmetry of it, but the coefficient encodes functional information that can depend on the geometry or other fields on the manifold. And this is where you're going to get the magnitude. It will affect this term here in the front, will affect the magnitude of your integrals involving these wedge products. So the wedge product, dx1 wedge dx2 wedge dx3, defines a three-dimensional oriented volume element, while the coefficient minus cos of the third coordinate x3 scales this element based on the coordinate x3. Now the fact that x3 doesn't appear in the wedge product doesn't matter. It simply reflects that x3 is influencing the magnitude, not the orientation. All right, so key points. Each term in omega is a product of a scalar function and a wedge product of differentials. The structure is completely determined by the dimension n of the space. Okay, that sets the upper limit. And the degree k of the form. Remember, k is equal to or less than n. Okay, but n sets the structure completely by the dimension n. That's as high as you can go. And that is our formula. All right. Thank you very much, everyone, for watching. I hope you found this useful. I hope you found it informative. I'll see you in the next video, but can I please ask that you push the like button and subscribe, please? That helps me out too, even if only as a matter of satisfaction. But it gives me a measure of whether or not people are finding the content useful. So I greatly appreciate you watching. I look forward to seeing you in the next video. Everyone, please take care, and best wishes to everyone. Okay, cheers.